We will discuss problems related to the workshop, and this discussion will be led by me and Yanping Huang. The participants of the discussions will be the speakers of the afternoon workshop talks, and those are Dani S Bassett from the University of Pennsylvania, Yoshua Bengio from the University of Montreal, Cristina Savin from NYU, and D.Duvenaud from the University of Toronto. And to kind of kick off the discussions and heat up a little bit, I start from a very generic question to all participants of the workshop, which is, what is the main motivation for you to study machine learning and or neuroscience? If nobody wants to start first, I'll just okay, Yoshua, you would like to start first, so I'll give first the voice to you, and then I'll ask the rest of the speakers to also say a few words. Thank you so much.
Sure. As I often say, this is what got me into these grad studies in machine learning. The idea that there might be shared principles of intelligence between animals and with the machines we could build in the future. And the idea that there could be a few simple principles like the laws of physics that, of course, would not explain everything in the brain, but think about how a few simple laws of physics give rise to very complicated phenomena in, biology or chemistry, right? So you can start from simple things. And so if we can discover those simple underlying principles, that would be amazing. And that's really saying that there is a synergy between the research going on in neuroscience and cognitive science on one hand, and in AI on the other hand. And because I believe that learning is so crucial to having a few simple principles, then machine learning is at the heart of the AI side.
Yoshua, so you mean it looks like there is a sort of pre-algorithmic stage, which means that instead of thinking as we usually do as computer scientists in terms of laws of nature, could probably be better for example, for perception, for language, for vision, or what else? I mean, pre-algorithmic in terms of
no. So I'm thinking of more general principles that would apply to any modality. Of course, when you consider specific modalities and specific tasks, you can always do better by putting in more prior knowledge. So there's a trade-off between generality and how powerful a particular inductive bias can be. So what I'm trying to say is, there's the no-frills theorem that says you do need some inductive biases, and we can get inspiration from biology for that. But then a big question that comes up, for example, if you heard the talk by Tony Zader the other day, was really nice, is where, should we put a lot of inductive biases or just like very simple a few principles? And different people have different taste about this. And obviously he and I are on different parts of that spectrum. But one aspect of the discussion that I had with him afterwards, offline and before, is that there may be an advantage to considering the inductive biases that involve few bits, and they're more likely to be applicable to a wide variety of domains. So think about animals that have no learning at all or very little learning. They tend to be very, very specialized in their ecological niche. And if something really changes drastically in their niche, they might not survive. Whereas like we are at the other extreme, and we basically have dominated all the possible niches on Earth. But that's he disagrees with me, so it's a hypothetical statement.
So do you think we need a new kind of mathematics for neuroscience? Just for example, in machine learning or AI, the core of the methods is multiplication, right? But we didn't know for sure like neurons can do multiplications at all. So do you think we need a new mathematics to connect the two areas?
No, I'm just say a few words about multiplication. I don't think that you need multiplication to be the building blocks. Multiplication is the building block in artificial neural networks because it's convenient. But every neuron in the brain does actually slightly different computation, which is not exactly multiplication. Something more nonlinear. And in fact, the operations that are being done are not exactly the same from neuron to neuron, which is actually one reason why straight backprop is not really biologically plausible, that nobody talks about this. You have the same problem in analog hardware that, the devices, the particular instances of different devices at different locations in your chip are actually doing something slightly different. So you can't have like homogeneous set of equations that describes what every device is doing like we do in artificial neural nets and then compute analytically the gradients. This wouldn't make sense for brains or for analog hardware. Instead, you have some device specific, like neuron specific nonlinearities, and of course it's of a type that's very similar between different pyramidal neurons, for example. But still, somehow the learning procedure needs to be able to deal with all of that variability.
Danielle, would you like to tell us what motivates you to study these disciplines?
Yes, I think I've been very interested in human cognition and what thought is since I was quite young. And I think my interests have stemmed mostly from the areas of philosophy. But then I think as I got older, I realized that in order for philosophy to tell us something more exact, we need to move closer to natural philosophy, which brings us to the sciences. And that's what led me to physics and to neuroscience. So I think it's still mostly about how humans think. I think that the work in AI and machine learning that we've done in the lab is sort of more for the purpose of understanding humans. I think that's really where my interests are. But I think that it's interesting to combine all of these ways of thinking about problems to understand thought.
So from what I'm hearing from both you and Yoshua, it seems like we are convinced that building artificial intelligence by looking at biological systems and trying to build the artificial systems by looking at those, it's the right way to go. Like, are we convinced that this is really the right way to go?
Well, I think it depends what the goal is. If the goal is to understand the human mind, then probably yes. Mm-hmm. If the goal is to have a lot of power to do some really wonderful things for our society, then maybe no. There are many ways, I think, for machine learning and AI to be very helpful to our society without necessarily following biological principles, right? So I think it depends on what your goal is. I think for me, the goal is the human mind. And so therefore, I'm most interested in mechanisms that are biologically plausible, but I think that there are perfectly reasonable goals to benefit society that are pushing us in other directions as well.
Mm-hmm. Before I ask David and Cristina the same question, Yoshua, can you just quickly comment on what I just asked? So just to repeat the question, do we really are convinced that in order to build artificial intelligence, we should look at biological systems as an inspiration?
Well, research is about exploration. Exploration needs to be diverse. So I'm happy that others are not looking at the brain. But I think it would be a missed opportunity not to look at the one family of successful intelligence that we have with all the brains across biology. Now, that being said, I think there could be a lot of aspects of biology which may not bear too much on the abilities of brains to give us intelligence or even consciousness or thoughts, but may matter for all kinds of biological reasons, energy, or just because this is built on top of cells, and so that's one aspect. The other aspect is if we take some things we observe in biology and we don't really understand why evolution put them there, it's probably not going to work to just copy that into artificial systems. So I think a big advantage of working on the synergy here is to force us to think about the why question, like does this provide an advantage for a learning agent? That's a very, very important question. So in that sense, AI research can be useful to prune theories about the brain.
David, would you like to share with us the motivation for your research interest?
Oh, I mean, just I think because intelligence is the one skill that unlocks all the others. But in the spirit of a spirited discussion, I want to reply to this idea about inductive biases. I understand the no free lunch theorem, and I understand it as a theorem, but I don't actually agree that it applies to the problems that we care about. And I would say something chauvinistic, which is that some priors really are better than others. And in particular, hierarchical.
I agree with that. I think the no free lunch theorem has been over interpreted in the way that you're suggesting, but I totally agree with you.
Okay, well then, so even though Yoshua agrees, maybe I'll just give a concrete example of what I'm saying is that if we have, for instance, 2 language models, one for English and one for French, I don't think we can decide which one is better. But if now a third one comes along that is a mixture that says, I'm uncertain which language I'm going to be processing, English or French, that prior has to pay an extra bit to learn which language it's speaking, but then it can speak either one. And that is just not strictly in every sense superior, but in every conceivable sense. And then if we take this to the sort of asymptotic limit, we end up with Solomonoff induction and these sort of universal priors that are incomputable, but they're still really great priors. That's all. I just wanted to add that.
So speaking of priors, so when we use implicit function theorem or like self-tuned networks, how do we incorporate the prior knowledge about hyperparameters in those methods?
Oh, well, the thing is, I would say these are purely optimization procedures, and we're estimating gradients. In fact, that's something I kind of was hoping we would talk about is like backprop, distinguishing the algorithm for estimating the gradients from the question of whether it's a good idea to estimate gradients in the first place. And I would say gradients are just so great. They give us this instantaneous counterfactual. I think Yoshua has talked about this a little bit. But as for how we estimate those gradients, I think the sky's the limit, and we shouldn't be constrained to like backpropagation specifically, like the chain rule specifically.
So in your opinion, what are the benefits of the gradients methods over for hyperparameter tuning over like zero order methods such as reinforce or random initialization or random selection?
I mean, if scalability, I mean, gradients just tell you so much more about the function that you're optimizing, as long as they're good estimates, right? If you're using reinforce, you're squeezing blood from a stone and you're still going through a one-dimensional bottleneck. So, just the fact that you have a gradient doesn't mean that it's useful, but if you can estimate it, it's giving you an amount of information that scales with the amount of parameters that you need to tune, which is exactly, well, that's a scale to these.
So I want to comment on reinforce because this is something that a lot of biologists believe is what's going on in the brain. The variance in the gradient estimator for things like reinforce grows linearly with a number of independent noise sources, the things that you're twiddling. And if you're going to use reinforce at the level of individual neurons, that means it's proportional to the number of neurons. And so think the noise is maybe spiking noise or whatever. And the number of neurons, of course, is huge, right? And so this one scalar is going to have the sum of all these 80 billion sources of noise coming into it. It's going to be, it's going to take 80 billion times more data to figure out the true, some direction of descent. So it's just hopeless.
So I agree with that. We had this conversation before, but I agree with that. That sort of like in the vanilla sense, reinforce at really large scales is not going to work. And I think there's a lot of interesting scope of sort of combining some notion of local gradient where you have that information.
Sure. I mean, it works in deep RL, for example. So if the space in which you're doing the reinforce is a small dimensional space, like a sequence of discrete actions, yeah. Or maybe it's modules in the brain, like maybe it's not end-to-end backprop, like maybe you've got local reinforced things, but then within each module it might be a sort of backprop like thing going on. I think that would work.
This is the where I'm at in terms of the space of solutions. I think the sort of like you don't have gradients to everything, so you can't sort of like backpropagate through a model of the environment and things like that. Even if you have a local model, it's still complicated. So there's some aspects where it's useful to sort of like get information about which way is good, simply by node perturbation-like methods. That being said, I agree that doing node perturbation end-to-end scales miserably, and you're not going to be able to do that. So I think the challenge is also sort of like with respect to sort of generalizing backpropagation to if there are sort of interesting hybrids that combine some of the gradient information that is relatively local with node perturbation for information that is not easily accessible through biological operations. I think that's a very exciting avenue, sort of where we don't have the math completely worked out. So there are some solutions that are definitely improvable, but that it feels in the right spirit.
Yoshua, there is a question for you in the Rocket chat that kind of links to some of the things we were mentioning. So let me read this question to you. You mentioned the operations done by individual neurons are nonlinear. Do you think that this is a bug or a feature? An example, is it a byproduct of the biological substrate that the brain deals with somehow, or at the nonlinear operations due to the dendritic tree structure, somehow fundamental to the rules that govern biological learning?
Let's see, the individual neurons are nonlinear. That's clearly a feature, not a bug. I mean, we know that. Is it a byproduct of biological substrate? I'm not sure I understand where the person is getting at. I mean, having the nonlinearity is clearly fundamental. Like this is a neural net 101. So I'm not sure what the question really aims at. Sorry.
So let's switch gears and tackle a different question, which is related to what you guys were talking about. So my next question that I had in mind to ask all of you is, what are the most fundamental differences between the learning process of biological system and neural networks? And in particular, I would be interested to see if there are some aspects of biological systems which are clearly not adapted in the context of neural networks. But if we borrow them for the word of neural network training, we can greatly benefit. Can you maybe make a comment? Christina, do you want to start?
So I can have a tentative answer to this. So I think locality of information, both in space and time, is very specific to biological circuits and not so much of a concern in the machine learning domain. Although sort of like if you're thinking about moving to different types of hardware, it might become a concern from a machine learning perspective as well. So for massive parallelization, that becomes important again. The other thing is that biology operates at a lot of different parallel timescales. So like synapses, we model them as a single scalar value, but in biology, they're like complex molecular processes that underlie that scalar value and that have complex implications on how the neuron processes information and how for subsequent experience might affect changes in the synapses. So all this metaplasticity discussion. And there's one example from Claudia Kloppat's lab where they show that if you add this kind of multiple timescale dynamics at the level of the synapses in the context of a continual learning recurrent neural net type of setup, you actually can get machine learning improvements of performance in some setups. So I think that it's maybe not obvious how to do in a general setting. It's also not clear how it helps, but there are some examples that I think are interesting in that domain. Yoshua, go.
There's a whole. I want to bounce on the things that Danielle talked about regarding thought, because I think that's one area where what we observe in especially human brains and maybe mammal brains to some extent. About conscious processing seems to be achieving a function that's super important that we don't have in machine learning, and that is the ability to quickly adapt to new situations by planning or using attention and focusing on just the right pieces of memory or the right pieces of perception in order to solve a problem that's new. And current machine learning is not good at this kind of out of distribution generalization. We can see humans doing it on the fly. We can see probably rats doing it on the fly. And there's a lot of neuroscience already about what is going on that hasn't been incorporated in machine learning. So I think this is an exciting area where we can import new ideas into AI.
Yoshua, Cristina, I would like to add a comment about what I feel is remarkably different when we compare machine learning algorithms and what happens normally in biology. It seems to me one remarkable difference, especially if you take, for example, take vision, for example, is that we don't really have the same temporal coherence that, for example, we experiment in vision, where instead of having something like ImageNet, you have a sort of coherence of the frames. And so if you think in terms of backdrop biological plausibility, of course, we all agree that it is not plausible, but there are some interesting contributions in the last few years where we can actually extend backdrop, think about, for example, equilibrium propagation. But don't you believe we are still missing models which properly deal with this remarkable continuity in time?
Absolutely. I mean, there are already very standard neural nets for video, but I think they're not exploiting the information nearly as much as they could. So one of the really exciting line of research that I think could make a difference in the next few years is the work on discovering latent causal factors that Apo Ivarinen has talked about at this conference, and he's been working on for a few years, making progress. Basically using time, for example, in order to help disentangle underlying causal factors that may be actually also dependent and not just independent. This is one of the, for me, this is one of the holy grails, like how does the brain figure out good abstract representations that capture the independently controllable abstract factors that make sense for a human in their environment. Probably, you know, it's also going to require dealing with the action perception loop. But I think that this is very different from the standard, you know, fixed data set, ImageNet, or even the way that we're dealing with video right now.
Yeah, I was just thinking about, you know, from a pure algorithmic point of view of the difference between backpropagation through time and backpropagation, or recurrent RLTL, real-time backpropagation, right? Where you see that whenever time is involved, something, you know, is missed in terms of from an algorithmic point of view. So it looks like something really new is needed, right? Because whenever you deal with temporal structures, it seems to be extremely more difficult. At least we don't have the same optimality that we have for gradient computation for feed-forward nets.
Right. So I think we need to distinguish the very short time scale of the kind that we do with equilibrium propagation, where we're thinking about, say, what is going on within a 100 millisecond frame where you have an input. And there's the dynamics of the brain that is computing something. So that's one thing that we don't pay too much attention usually in machine learning, but I think we should. And by the way, it's going to help us to deal with things like decisions, symbols, and all kinds of interesting things. But there's also the longer time scale where memory becomes involved, and where you would normally use backprop through time if you wanted to deal with these long-term dependencies across like minutes or hours or days or months or something. And backprop through time, you know, through months of life obviously is not plausible. So what my group and I has been working on in the last few years, and we're still working on, is using memory. And you know, the brain has memory, many kinds of memory. And when you recall something from memory, you're creating a connection through time that you know breaks the long chain of small dependencies that you would normally look at in backprop through time, and creates a direct connection between some arbitrary past and the now moment. And you can kind of backprop through that immediately to do credit assignment, to say, well, 2 hours ago, I didn't notice that there was a funny sound when I was driving my car, and now I see that I have a flat. It was probably that, I hit something on the road, and I should have stopped, right? So this is credit assignment. If you were to do it with normal backprop through time, it would be crazy because 2 hours have passed and so many things could mess up the gradient. But if I use memory, it connects these the past and the present in a way that makes it much easier to deal with credit assignment. So I think this is the sort of mechanism that's biologically plausible. We do remind things all the time, and I think that's part of our credit assignment mechanism through time.
Danielle, would you like to add a comment to the discussion? So just to remind you the question that I had in the beginning that ignited the discussion, I was asking whether there are some mechanisms in biological systems that we currently do not pay attention to when training neural networks and computational models, but if we actually pay closer attention to them, we may really greatly benefit in computer science. Can you make a comment?
Yeah, I mean, I think I enjoyed all of the responses thus far, and I do think that the time dependence is something that is multiple timescales of time dependence is something that's quite important. I think that there's also something to be understood about the structure of temporal information in the world around us that is not always accurately depicted. In fact, is most often not accurately depicted in movies. And so if we're using movies as training paradigms, that may be a very important simplification of the problem that real neural systems have to face. And so I think that trying to understand the temporal architecture of information in the world is going to be an important dimension to progress.
I would like to ask a question now from a completely different kind of poll. So this is the question that I first target to David. David, I don't know if you remember, but the first time we met, I think was in Harvard, right? You were a student there and I was giving a talk. And at that time, I remember both of us were extremely excited in the research on surfaces of deep learning models, which is a topic that actually still excites me very much. But so we saw that the study of error surfaces used to be a very hot topic about 5 years ago. And then it a little bit vanished. It kind of disappeared from the spotlight. What do you think is the reason for that? And do you think it deserves a comeback? So I want to ask first David for that.
Sure, I guess I'll just say, I do think there's been a huge amount of understanding in how optimization proceeds in deep learning in the last 5 years. And I think actually Roger Gross, I wish he was here because he's really the sort of expert on this that I work most closely with. And I think like part of the answer is that we sort of now see that whether using natural gradients or not, or like these other sort of slightly different parameterizations make such a huge difference that it's almost silly to examine the loss surface until you've decided which sort of parameterization you're going to use. And I guess I'll just say we also started to have these tools like cheap Hessian vector products that are easy to implement and they don't require James Bartons to write like 5,000 lines of MATLAB. But I think there have been the papers that asked all the obvious questions about those have been written over the last 5 years, and I stopped working in that direction because I thought like all the obvious ideas have been done and I don't have any more. So
I can say something as well. So what I think is it's not quite about the geometry of the energy landscape, but I think it's closely related. Is that people in the context of Bayesian deep nets are starting to think about the geometry of the posteriors over the parameters and how the architecture or the statistics of the data influence that. So there's some really cool work by Andrew Wilson recently, who sort of like shows that there's really low dimensional and relatively exploitable structure in the correlations between it's a really highly correlated space, and sort of like much more lower dimensional than the apparent dimensionality of the parameter spaces. And I think that's really exciting because it's sort of like it forces us to think about different ways of representing the learning dynamics and different ways of maybe doing approximations in that manifold of sensible parameters.
So it has also an impact in continual learning, just to add to your comment, because understanding better how the surface is being explored has almost enormous impact in understanding how, when we add new tasks, how this task can share a common parameter space. So that is something that that is the work that I'm currently doing in my lab. So that has also very, very, very important implications. Okay, so I wanted to also ask a question regarding continual learning, also in the prism of maybe biological plausibility. And so in particular, in continual learning, I will just say one word in continual learning, right? What we want to really achieve is to make learning machine learn different tasks that come in a sequence, but in this way that we are not forgetting the previous tasks, right? So as we acquire new experiences, new information, we want to preserve the information that was already acquired, and also we want to transfer knowledge between the tasks. So there's some information that we can use to solve a new problem, then we want to this information to be preserved. Now, there are various ways to tackle continual learning in the literature. Partially, I feel they are maybe inspired also by biology, like, for example, architectural solutions, where the idea is that when you learn new tasks, you expand the architecture, so you accommodate, you grow the capacity in order to accommodate new tasks. But there's also this notion of compressing the architecture after that, so that you control the growth of your model, and that has some parallel to neurons being born and then dying in the brain. Other approaches, strictly optimization, which are basically aiming to try to design the optimizer in such a way that more than one task can be accommodated. And of course, the third family of methods are methods that rely on memory. So basically replaying old experiences. So as you learn a new task, you still have a replay strategy that sort of reminds you what was seen before. So we also know that continual learning is, so far it doesn't work very well unless we have very similar tasks, mostly like mnist and permuted mnist. So I'm just always wondering, because it seems like all the strategies that we have in continual learning are more or less maybe biologically inspired, maybe not. But the question is, do you have some insights from your experiences in various fields that you all of you are working on, how to solve maybe or tackle this problem in a new way? Do you have any insights to that? Cristina, you mentioned continual learning before, right? So that is a topic that that's important for us, for machine learning people. So Yoshua, do you mind if I start with you? And
sure. Yeah, it's a very interesting topic. And I would start by making a comment that we typically think of the continual learning setup as a hindrance. And instead, I'm thinking of it as an opportunity for the learner. If you think about trying to understand the causal structure of the world, having changes in distribution that are natural, like that are arising because something happens, like maybe somebody tells me to do a new task, or maybe something changed in the world and the way to solve problems is now different. It is actually an amazing source of information for a learner which tries to figure out the underlying causal structure of the world, because if you can learn how to infer what was the change, or just if you can learn to decompose knowledge along its underlying causal mechanisms, then you become much more robust to those changes, in the sense that either you don't need a lot of data to adapt to a new task, or in fact, you might do inference to explain the change, and then it's instantaneous almost to adapt to that change. So what I'm trying to say is that when you have these changes, they contain information that you would not get if the data was simply mixed and IID, and the way that we usually do machine learning. And we should see this as a bonus. Now, the part about forgetting because of the, if we do SGD, I think we're paying too much attention to this. The brain has a huge amount of memory, and we can do replay. The real question about this is we can only replay so many things, and so we have to choose what to replay. So I have, my intuition is that evolution probably combined with learning possibly figure out a policy for replay in the brain that just, gets the right, interesting things from memory that you need to replay. And that's something I don't think anybody's done in machine learning, right? We're trying to hack something that will work, but we could just optimize it.
Well, I guess we don't fully also understand the sleep. I mean, I'm not an expert in the biological systems, right? But I think we also don't understand really the role of sleep in the, development of brain, right? Which I don't know, maybe replay happens also during, some sleep phases or so, right? We don't really understand that as well. So, yeah, but that's a great answer. Danielle, right, and then Cristina. Okay, Daniela, can you?
Yeah, sure. So I also think that the other really key component that's present, at least in the human brain and some other animals, is the capacity to control lower level dynamics from a higher order system. So from the frontal parietal circuitry, for example, and the control signals that are used by that system can guide the system to move back and forth between different learning strategies or between different tasks, or there is a hierarchy here that I think is important to consider. And the link between controllability of a network and learning, I think is very important, and something that we haven't really capitalized on as much as we could in the field. So I think, yes, it definitely is about memory, but it's also about the very transient, quick control signals that allow us to use a different piece of circuitry or a different pattern of activity on a bit of circuitry. And that hierarchical system, I think we could consider operationalizing more in the AI methods we use.
So by low-level dynamics, do you mean ion channel dynamics? So so there is a gap between, for example, how action potential can propagate fully ion channel dynamics and how continual learning could happen in the brain, right? So do you suggest that we need to look at the molecular foundation of learning in that level, in the molecular level?
That's not exactly what I meant, although I wouldn't dismiss it. I think that what I meant was controlling activity and, well, engaging some control on lower level, in the sense of lower level processes. So like unimodal processes of vision, audition, or motion, and higher up in each of those streams as well, but not to the degree of these control circuits.
Yeah, thank you for clarification.
Christina, on to you.
So I think sort of like people have started to put attention in as a way, or attention-like circuitry as a way of top-down controlling the flow of information through through hierarchical circuits, and I think that hasn't really been explored enough in the context of learning, or in context specifically in the context of continual learning. So I think that's an excellent point. I had a couple of sort of more big picture, very quick comments, and then we can go on. So first of all, yes, the brain needs to learn from a lot of tasks in order to build representations that are suitable for solving a range set of problems that it needs evolutionarily to solve. I don't know that it does it the way we're setting up our continual learning problems to work, in the sense that it's not like I only have to deal with this task for a while, and I only have to deal with this task for a while, but rather there's a distribution of the tasks, and those are interspersed in interesting ways. And the brain does forget about tasks that are no longer relevant. So I think so, sort of like we're maybe setting ourselves up for failure by making the requirement of what we mean by continual learning a little bit harder than it strictly needs to be. Yeah, so that was my thought.
David, so I want to ask you, since we are in this topic of also continual and online learning, I would like to ask you specifically a question. If you see a connection between hyperparameter learning and meta learning, can you comment more on that? And also, if you want to add to the previous discussion.
Oh, totally. Yeah. So I guess I would say, they're both nested optimization problems.
Mm-hmm.
And so we can try to amortize the inner optimization or its gradient estimation. And that, I'm not sure that makes quite as much sense in the meta learning setting as it does for the hyperparameter optimization setting. Because if we're doing a hyperparameter optimization, we can say we really just need to know what the sort of the gradient is right around where we are, so that we can then, move our hyperparameters in that direction. If we wanted to do something like MAML, where we replace the inner optimization with some sort of amortized like hyper policy or something, we could certainly do that. But I think generalization is where we would suffer. Like if the tasks are very, very similar to each other and the policies are similar, then we can totally amortize this into like a network that takes in the task description and outputs a policy. But the beauty of general purpose optimizers is that they work on totally different problems than they've been trained on. So that's the trade-off. It's basically just speed versus generality.
So David, I had a question about this part of your presentation. Since really what we're trying to do with hyperparameters is a search, shouldn't we have the hypernetwork be stochastic? And then basically it's generating a distribution over hyperparameters and we optimize the parameters of that distribution?
Yes, so because my talk was so short, I had to skip over that. But for the hypernetwork version, you actually do have to add a little bit of stochasticity to the hyperparameters in order to give a learning signal to the local hypernetwork. And that's one of the drawbacks of that approach. So I'm actually, yeah, so you totally saw the the little gotcha. Anyway, I'm impressed but not surprised. So yeah, so that's kind of a downside of that approach. But I don't think it's a killer in high dimensions. So.
But if you could make it even more stochastic if it was even multimodal, right? It keeps track of the good solutions and explores, right? So instead of having a Gaussian, you imagine have like a VAE-like thing or something, right?
Oh, exactly. I mean, the thinking behind following a simple gradient descent approach is that we're going to sort of lazily inherit the goodness of over-parameterization, and just the idea we'll avoid local optima by just somehow finding a million hyperparameters, and then we don't have to rely on finding other modes as much. That's the hope, anyways, and it seems to sort of work. The thing is, where that research lies is that we got it to scale up, but we haven't actually really probed the limitations of like, well, can we not scale it up more just because of like variance in the gradients, bias because of our estimators, local minima? We're not actually sure what the limiting factors are right now.
But I mean, can you think of a biologically plausible version of hyperparameter optimization? That's where I'm getting at, right? I mean, the brain can't run 50,000 trials in parallel. So, but it could sample from a distribution over hyperparameters. And in fact, they might be context dependent, which is what, I think we observe in biology. So it does make sense to have a hypernetwork, but it would be a stochastic one. I don't know.
Well, I do want to say this hypernetwork isn't stochastic in the sense that its outputs are stochastic, just that we need to give it some variation in its training data.
Yeah, I understand that part.
Okay, great. Yeah, so then I guess I would say, I do think that it's, I think amortization is probably happening all over the place in our brain. But yeah, I mean, I think it would be a waste of time for me to speculate on a panel with actual neuroscientists. So.
Yeah, so I think it's funny that you're sort of advocating for reinforcing the hyperparameter space when you're so against it in the parameter space.
Oh, wait, well, I'm not actually.
Not you.
Oh, great, okay.
Not your fault, David, don't worry about it. No, I mean, it's true that maybe the hyperparameter space is sufficiently small and sort of like more factorizable in a way, especially if you think about it from a biological perspective, that the hyperparameters are definitely not globally accessible, so they're relatively local. That's why we were playing with the sort of like hyperparameters that are parameter specific. So like having very local learning dynamics that you adapt on.
Cristina, you muted yourself.
Actually local then maybe reinforcing something like that is actually not as bad, so the variance doesn't scale the same way.
So actually, we have a related question in the chat room. It's posted at 5:32 p.m. Related to perturbation-based methods and their inability to distinguish contributing source of variation and not scale well, what would be your take on the concept of discovering a representation of the parameter space such that performing a perturbation in such a representation space would sample a gradient step?
I like that.
Can you translate?
So
like,
can we, yeah, sorry.
My interpretation of it is sort of like, again, sort of like this idea that there's a lot of correlation in the parameters, and there's actually a low dimensional representation of the parameter space in which you actually want to do perturbations. So you don't want to do perturbations in the billion dimensional space. You want to do perturbations along the manifold because that's the interesting part of the space. So if that's what he meant, then yes.
Yeah, but even if you reduce dimensionality because there's maybe redundancy in the brain, I mean, isn't that, you're not going to go from 80 billion to 10, right? So I don't know.
As I said, for the Wilson experiment, it seems like they end up with relatively low dimension, like quite low.
No, but of course, it's always, when you consider only one task, which is typically what biologists look at, there's always a low dimensional manifold because you're only considering those trajectories. It's kind of obvious it's going to have to be that way.
Not in parameter space necessarily. So I think sort of like having more tasks might actually restrict the parameter space.
No, even in parameter space, because the number of independent bases to explain the trajectory cannot be more than the number of examples, for example. And it's probably much less.
So I got the information that we need to wrap up. I need to finish in about a few minutes. So
I have a question.
Okay, Marco. So a quick question, and then one more from me, and then we're wrapping up.
It could be a question for all the speakers, but I was stimulated when Yoshua said that artificial intelligence can prune theories about the brain, right? So just wonder, if you ever considered, what we know from developmental psychology. People from the developmental psychology know that the evolution of children in terms, for example, of vision is such that there is a gradual, let's say, increment of the visual acuity. So as it looks like, newborns are protected from information overload, right? So don't you believe, and it's for all of you, that we are probably still missing this important point, right? So learn, and at the same time, to protect ourselves from information overloading, which could be also connected somehow to focus of attention.
I think you have phenomena that happen in existing algorithms, like the dynamics of learning, which are self-regularizing. It's one of the discoveries of recent years, right? That you can have a large network, but the SGD dynamics are going to prevent it from overfitting, even early on. And that could lead maybe to phenomena like this, or maybe it's something that's been built in by evolution. There was also what I think Carl Friston was talking about, where there's sort of a automatic trade-off between exploration and exploitation that comes out of an objective function. So things like that can happen as a side effect of the optimization process, or it could be built in by evolution. It's hard to say. But what I was trying to say in my sentence was, when you want to have a theory about some aspect of neuroscience that is mechanistic, that we can actually implement the computation, I think a good test of it is, is it able to learn the kind of complex tasks that we can learn with machine learning, or that brains can learn, and that's just a test, right? Which you can derive in many ways.
And in this case, do you think that principle from curriculum learning could also help somehow?
Yeah. And as I was saying, we don't know if curriculum learning is arising out of a predefined program from your genes, or it's a side effect of something more fundamental. Both are possible, but there is obviously, I mean, Piaget has been shown right. So,
yeah. Okay, thanks.
So last question, and we will be wrapping up this question, non-technical question. So we are living in a field in machine learning where the acceptance rates are low. There is a very randomized revision system. Your advice to young people who want to make splendid careers in machine learning. I'll ask all of you to just give a quick word of advice. Daniel, and in neuroscience and in machine learning, how to overcome the competition and be recognized. Daniel.
Wow. I think that maybe it sounds trite, but I think the biggest thing that you need to do is follow the important questions and also be willing to wait. I think that sometimes the pressure to publish is so hard and so high that lesser ideas are published more regularly. And I think waiting, as hard as it can be, is really important. And so I guess I would just say to remember the value of science and obviously do it with integrity.
Wonderful. David?
Oh, I guess I would just say that there's great mentorship everywhere. And, I think when students get into this field, they don't know who to trust and who's going to be good, except to just go for like big brand name schools and advisors, which of course doesn't scale. So on my webpage, I have a list of like, if you like me, you'll also like these other people, including a bunch of people at like less famous institutions. It's like a very sensitive thing though, right? I'm sure I'm hurting lots of people's feelings who aren't on my list. And maybe it's for a silly reason, or I just didn't remember them or whatever. Like, I think there's a need for some sort of pseudonymous feedback, because I can't in my grad courses, I like criticize papers very freely. And I say, oh, like, this whole approach seems silly for this reason, but I'm not going to go on Twitter and say that. I think, anyway, I'm just saying one thing that I think is hard is for young students to know how to trust. And I would love for people to like brainstorm ways that we could sort of give them more honest information about that.
Thank you, David. Cristina?
Yeah, my policy has been always to do stuff that actually interests me and just hope for the best. So far it's worked, but I don't know if that I will ever recommend that in a general panel. So go with the important questions, do good work, and hopefully the system is self-correcting and that will be recognized along the way. I think people are sort of, maybe there's too much pressure to demonstrate outcomes immediately overall, and that's not something that we can change on a immediate time scale. So it's part of life, but if everybody operates that way, hopefully it will self-regularize.
Thank you so much, Cristina. And Yoshua?
Well, I'll go with it, Danielle's advice, but your question was about the individual. I would say maybe we should also think about the collective rules of the game, and that we can change those rules, especially senior people like us around the table. And there are ways to change the publication process, the review process, that could favor slow science, long-term problem solving. I think the current conference-based system that puts a lot of weight on significance during review is introducing too much noise. It's creating a lot of stress and pressure for short-term results as we go from one deadline to the next deadline. I think it's time to rethink the whole thing, and I wrote a blog about it, and I gave a talk yesterday in the a pre-registration workshop about some of these ideas.
Thank you so much. So we have to finish now the discussion. So our speakers were Yoshua Bengio, Daniel Bassett, D.Duvenaud, and Cristina Savin. And I just want to remind all of you that together organizers and speakers would like to meet on Gather Town. I believe we want to have like a group, a virtual photo. So I invite all of you to join. It's going to be on Gather Town, room 2, under the Christmas tree. So we're going to be waiting there for you guys now. And we hope to see all of you for a group photo. Thank you so much. Thanks for your attention.